Playing with numbers in Drake's equation has showed us that intelligent life forms may be few and far between. The nearest civilization may be thousands of light years away, if we are lucky. Finding a candidate among our closest neighbors must be considered extremely unlikely. But don't you know that there is an Earth-like planet in our neighborhood, located just 4 light years away? It's Proxima b. 8 years ago, the whole world of science news was recently abuzz with discovering the closest alien planet to our solar system. While the detection seemed solid, more confirmation is always good. And now the James Webb Space Telescope has provided that extra and more detailed confirmation. In an extraordinary observation, the Webb Telescope has just announced the clearest image of Proxima b in history, revealing an astonishing discovery that could change everything we know about the universe and life on Earth. Join us as we dig deep into the mysteries of Proxima b and discover whether it could be the next Earth. As shocking as it sounds, we find exoplanets, or planets orbiting stars other than our Sun, all the time now. We know of nearly 6,000 such planets, plus another 10,000 planet candidates. So what makes Proxima b so particularly exciting? First off, Proxima Centauri b is of particular interest since it's orbiting the closest star to our Sun, only 4.2 light-years away. Its confirmation underscores current findings that such worlds are common in our galaxy. Proxima Centauri b is very similar in size to Earth, with a mass of 1.17 Earth masses. It orbits its star in only 11.2 days, in contrast to our Earth's year-long orbit around our Sun. That means Proxima Centauri b is a lot closer to its star than Earth is to the Sun. But because the star is a red dwarf, much smaller and cooler than our Sun, its orbit is indeed within the habitable zone of Proxima Centauri. Interestingly, Proxima Centauri b receives about the same amount of solar energy from its star that Earth does from our Sun. So, theoretically, Proxima Centauri b could have water on its surface. It could be habitable, but, of course, we don't yet know all the details about habitability for exoworlds. We do know that many factors affect a planet's habitability, such as temperature, composition of the planet and atmosphere, water, and radiation from its sun. Red dwarfs like Proxima Centauri are known to emit flares, and these flares make habitability for red dwarf exoplanets even more complex and interesting. Worse, our usual methods for detecting biosignatures won't work with Proxima Centauri b. Most exoplanets are discovered through the transit method, where a planet regularly passes in front of its star from our point of view. We see the recurring dip in a star's brightness, and we know the planet is there. For transiting exoplanets, we can look for changes in the spectrum of the star as the planet transits. Some of the starlight passes through an exoplanet's atmosphere, and some wavelengths get absorbed by the atmosphere. By looking at the pattern of absorption, we can fingerprint different molecules. This is how we've detected the presence of water, carbon dioxide, and other molecules in exoplanet atmospheres. But Proxima Centauri b isn't a transiting planet. It was discovered by a different method known as Doppler spectroscopy. When we look at the light from Proxima Centauri, we can see its spectrum redshift and blue shift slightly over time. The gravitational pull of Proxima Centauri b makes the star wobble slightly. So we know the exoplanet is there and have a good idea of its size and mass. But since it doesn't transit its star, we can't observe its atmospheric absorption spectrum. Fortunately, there is another way we might find life. From space, the most obvious sign somebody lives on Earth is the glow from the night side of our planet. Our cities emit light that's shed into the cosmos. The lights could be seen by telescopes on distant worlds if they truly exist, and vice versa. We Aslo could tell alien technology exists on another planet in the similar way. In principle, the idea is simple. Rather than looking for light passing directly through the atmosphere, look instead for light that has reflected off the planet directly. We've done this for planets such as Mars and the outer planets, which don't transit the Sun, so we could do it for exoplanets as well. For example, we may be able to see the light of a distant world waver with the transit of a massive constellation of satellites. Atmospheric pollution may be detectable from nuclear conflict. But while these indications of technology could also be caused by natural phenomenon like orbiting debris or a comet impact, artificial illumination is distinct from the natural light of stars. The problem is that reflected starlight from a planet is tiny compared to the radiance of the star itself. Detecting the reflected light of a planet is like capturing the light of a firefly flittering near the edge of a spotlight. Luckily, we are living in the golden age of astronomy. Today, we have a new generation of telescopes that are powerful enough to see lights on distant worlds. One of them is the James Webb Space Telescope. Scientists scaled artificial illumination as a fraction of the solar illumination, reflecting from the day side of the planet. 0% on this scale would assume that the night side of the planet is completely dark, devoid of artificial illumination. 100% means the night side of the planet is as equally bright as the day side. The type of light used by the hypothetical civilization on Proxima b is assumed to be similar to LEDs on Earth, which have a distinct artificial spectrum. The results? If the artificial night-side illumination of Proxima b reaches 5% of the natural day-side illumination, James Webb could detect the artificial light with 85% certainty. And if artificial illumination were to reach 9%, the Webb telescope detection confidence would rise to 95%. But James Webb turned out to be much better than we anticipated. Webb's mirrors collect light from the sky and direct it to the science instruments. The instruments filter the light or spectroscopically disperse it before finally focusing it onto the detectors. Each instrument has its own detectors. The detectors are where photons are absorbed and ultimately converted into the electronic voltages that we can measure. Webb needs extraordinarily sensitive detectors to record the feeble light from faraway galaxies, stars, and planets. It needs large area arrays of detectors to efficiently survey the sky. Webb has extended the state-of-the-art for infrared detectors by producing arrays that are lower noise, larger format, and longer lasting than their predecessors. Thus, in a recent observation, James Webb has focused its sharp eyes on the closest alien planet to our solar system. New insights obtained from James Webb have dramatically increased the amount of data on exoplanets and their atmospheres available to researchers. We all know that Proxima b, like our planet in several ways. But there are many ways we know that it must differ from our planet Earth, including it must be tidally locked to its star, where the same face always faces the star and the same face always faces away. It will have 3 climate zones, an ultra-hot one where it's always sunny, an ultra-cold one where it's always night, and an on-the-border one where it's always sunset, sunrise, and the solar flares coming from the star will potentially be a danger for stripping the atmosphere away. Of course, we can concoct scenarios where the planet hangs onto or replenishes its atmosphere and has conditions conducive to life. But this is nothing more than wishful thinking. In reality, we do not even know whether this planet is Earth-like or Neptune-like. The typical border between an Earth-like world, where you have a rocky surface with a thin atmosphere, and a Neptune-like world, where you have a large gas envelope surrounding your world, is about 2 Earth masses. Proxima b has a minimum mass of about 1.3 Earths, but that's if the alignment is perfectly edge-on. Since there's no transit, we know the alignment cannot be exactly perfect, but how imperfect is it? That's gloriously unknown. If the alignment is inclined at more than about 25 degrees from our line of sight, it's likely to be a gaseous world, not a rocky, Earth-like one. But at this point, without further information, we cannot know. If we were going to be as accurate as possible, we would state that there is a planet with an orbital period of 11.2 days, orbiting the closest star to us, Proxima Centauri. It receives 65% of the solar energy that Earth receives and has a minimum mass of 130% the mass of Earth. That's it. That's all we know for certain. If we wanted to speculate, we could discuss all the reasons Proxima b is likely to be inhospitable to life, what challenges this planet faces if it wants to achieve habitability, and what we'd have to measure to know for sure. But the truth is that we don't know any more than this. Until we have better, more comprehensive data on this world, all we know is its period, the energy it receives, and its minimum mass. The age of exoplanet astronomy is upon us, and although the search for city lights on habitable planets may sound speculative, it is worth pursuing as a potential technosignature with planned instruments. It is possible James Webb will detect far less illumination or see the same on much more distant exoplanets. Proxima b orbits its star every 11.2 days, providing 32.6 more opportunities for its possible inhabitants to celebrate their birthdays than we have on Earth, once per 365.2 days. The high demand for bright lights during birthday parties on the night side of Proxima b would be a reason for us to celebrate as well, if the signal was noticed by future telescopes. Once signs of life are found, sending a probe on Proxima is needed. But of course, a lot of technical challenges need to be overcome before we can hope to mount such a mission. In addition, a lot of questions need to be answered. For example, what kind of ship should we send to Proxima b or other nearby exoplanets? How long would it take for us to travel to it? The vast distance that separates us from Proxima b is terrifying. Compared to other regions of the cosmos, Proxima is almost in our backyard, but it would take approximately 78,000 years to go there with present technology, a calculation based on the maximum speed attained by our fastest probe, New Horizons, which was 59,000 kilometers per hour. If we wanted to reach Proxima in a reasonable 20 years, a spacecraft would have to travel at an average speed of more than 300 million kilometers per hour, which is about 28% of the speed of light. Regardless of this challenge, humans always strive to one day reach out and touch the stars. And it appears that even NASA has decided to visit there before the end of this century, with a project that is facing stiff opposition in some scientific circles, but which the American Space Agency believes it can launch by 2069. A date that is definitely not coincidental, as it recalls an event that occurred exactly 100 years earlier. That would certainly be a thrilling feat. To fulfill this dream, NASA will need a speedier method and more efficient technology to reach at least the nearest stars. Reaching the Alpha Centauri system in an acceptable amount of time would necessitate the development of a propulsion technology capable of at least 10% of the speed of light. The greatest challenge is storing the sufficient fuel load to enable the spaceship to accelerate steadily to the desired speed threshold. In spite of the seemingly insurmountable obstacles, numerous interplanetary spacecraft designs have been presented during the past few decades. In the 1960s, research and tests were done in the United States as part of the Orion project. The basic concept was to use the shockwave produced by the consecutive detonation of numerous tiny nuclear bombs to propel a spacecraft at high speed. Someone understood the project's potential for interstellar travel as well. Originally, the project was intended to transport massive masses into orbit or permit human journeys to Mars, but someone recognized its potential for interstellar travel. In the initial design, the Orion intended to rapidly release nuclear fission bombs, which, when detonated directly behind the vehicle, would give it a large boost via the impact of the shockwave formed on a unique shield capable of absorbing the shock without harm. Nevertheless, this notion, which would alleviate a number of the aforementioned issues, remains speculative and may be used to launch small probes to the stars. During the same time period, American physicist Robert Bussard presented an innovative solution to the mass problem by omitting the need for propellant. Thus was created the concept of the interstellar ramjet, a vehicle capable of gathering the hydrogen present between the stars and utilizing it to power a nuclear fusion engine. The collection of interstellar hydrogen would not be simple, in addition to the challenges posed by the construction of the engine. In fact, assuming an average density of 1 atom per cubic centimeter, to gather 1 kilogram of hydrogen at 1/10 the speed of light would require a funnel with a mouth of 5,000 kilometers in diameter, and the collected stuff would still be minimal in comparison to the requirements for propulsion. Interstellar ramjets, in all of its proposed forms, are therefore not regarded physically possible. In the 1970s, the British Interplanetary Society, led by British aerospace engineer Alan Bond, did a comprehensive study of the Daedalus variant of the Orion concept, possibly the most realistic interstellar ship design ever envisioned. Instead of nuclear weapons, the Daedalus was designed to utilize a succession of micro-explosions generated by the nuclear fusion of miniature deuterium and helium-3 tablets. The 2-stage, fully autonomous spaceship may have reached 0.1 constant, or 10% of the speed of light, with a launch mass of 50,000 tons, 93% of which was propellant. This would have allowed it to reach Proxima in slightly more than 30 years, then broadcast the data obtained during the flyby back to Earth. However, very innovative solutions are required to handle the issues of energy consumption and journey time. Since its conception in the first half of the 1980s, the interstellar sail concept has undergone a number of revisions and enhancements, mostly to reduce the energy requirements of the journey and make its operation more realistic. In any case, the main parts of the system would be a very powerful laser or microwave transmitter, which would probably be in space, a giant lens that would focus the radiation into a very narrow beam, even from a long way away, and the interstellar sail itself, which would be able to catch the radiation and speed up a lot because of the pressure it created. And by sail, we do not mean a racing spinnaker, but something more like anything at least 6 kilometers in diameter and just 30 grams in weight. Accelerated to 0.2 constant in only 2 weeks, Star-Wisp might reach the Alpha Centauri system within 21 years. Antimatter propulsion is another conceivable method. We know that when 1 gram of antimatter is turned into energy, it produces an enormous amount, around 70 times the energy produced by nuclear fusion and 4 billion times the energy produced by burning oil. Such an engine would enable us to reach approximately 40% of the speed of light, reducing the time required to reach Alpha Centauri to less than a decade. However, antimatter is currently scarce in nature and difficult to capture. Therefore, it is necessary to manufacture it, which is carried out in minuscule amounts in huge particle accelerators. Making engines for space exploration would take many kilos of it, however. This appears to be a negligible amount, yet it is significantly higher than what has been synthesized to date. Consider that it would take 1 billion years for an accelerator's antimatter factory to manufacture a single gram of antimatter. The conventional energy necessary to manufacture a few kilos of antiprotons every year corresponds to a total energy consumption of around 50 billion watts, which is equivalent to the power output of all nuclear power facilities in the United States. Currently, this is our scenario. We wish to visit the planet Proxima b, but we do not yet know how. Our technology is essentially still in its infancy, despite its tremendous development. No one can foresee what the human race will be able to accomplish by the fatal year 2069. But if growth continues at the current rate, along with many new issues to be solved, we will have vastly improved our abilities in precisely those fields essential to interstellar travel. Initially, expeditions to the stars will likely be done by intelligent robotic probes capable of moving at 0.1 constant and shrunk beyond currently imaginable limitations. As proposed by physicist Frank J. Tipler and described in Arthur C. Clarke's engrossing novel, The Songs of the Far Earth, even with simple probes such as these, humans could rapidly propagate throughout the galaxy, as a result of the extraordinary progress being made in the fields of biotechnology, genetic and molecular engineering, embryonic development, and cell physiology. In practice, this would involve the creation of so-called von Neumann probes, that is, intelligent automatons that, upon arrival at their destination, would be able to construct copies of themselves and habitats for eventual living beings, including humans, synthesized in situ from the genetic code and instructions for the generation and development of embryos. After initiating the successful colonization of a planet, von Neumann's probes might construct new interstellar spaceships and automatons that would go to other star systems to repeat the feat. Obviously, we are discussing little probes and seemingly science fiction at that. But NASA will have to take into account the fact that interstellar flight with humans on board will involve mass and energy scales thousands to millions of times larger. Current understanding leads us back to the concept of interstellar arcs, which are massive, environmentally self-sustaining dwellings capable of traversing the stars for thousands of years, while numerous generations of humans, animals, and plants follow within them. These arcs might be modeled after the massive space colonies studied by physicist Gerald O'Neill in the 1970s and launched into interstellar space at speeds as low as 0.01 constant. It is impossible to conceive of the circumstances and motivations under which humans might embark on a voyage knowing that they would never reach their target. Probably only the gradual uninhabitability of our planet and other inhabited solar system planets might motivate people to make such an extreme choice. If it were possible to considerably lengthen human life or slow down metabolic processes during flight, and achieve at least 0.1 to 0.3 constant with the requisite big spaceships, the conversation would alter drastically. For this to become a reality, however, it will likely take several more centuries, unless physics continues to surprise us in extraordinary ways. How then will NASA fulfill its obligations? Could it have a card up its sleeve? We simply have to wait till 2069 to find out. In addition to observing Proxima b, scientists also expect James Webb to turn its eyes to other Earth-like planets. Discovering the first true alien Earth is a long-held dream of astronomers, and recent exoplanet discoveries have shown that small rocky worlds like our own are abundant in the galaxy. To qualify as potentially life-friendly, a planet must be relatively small and therefore rocky and orbit in the habitable or Goldilocks zone of its star, which is loosely defined as a location where water can exist in liquid form on a world's surface. When telescope technology improves, other factors will be considered as well, such as the planet's atmospheric composition and how active its parent star is. While Earth 2.0 remains elusive, here are 9 exoplanets regarded as the most Earth-like alien worlds discovered to date. 1. Gliese 667 cc. Gliese 667 cc lies just 22 light-years from Earth and is at least 4.5 times as massive as Earth. Gliese 667 cc completes one orbit around its host star in a mere 28 days, but that star is a red dwarf considerably cooler than the Sun, so the exoplanet is thought to lie in the habitable zone. However, Gliese 667 cc, which was discovered with the European Southern Observatory's 3.6-meter telescope in Chile, may orbit close enough in to be baked by flares from the red dwarf. 2. Kepler 22b. Kepler 22b lies 600 light-years away. It was the first Kepler planet found in the habitable zone of its parent star, but the world is considerably larger than Earth, about 2.4 times our planet's size. It's unclear if this super-Earth planet is rocky, liquid, or gaseous. Kepler 22b's orbit of 290 days is pretty similar to Earth's 365. The exoplanet orbits a G-class star like our Sun, but this star is smaller and colder than Earth's. 3. Kepler 69c. Kepler 69c, which is about 2,700 light-years away, is about 70% larger than Earth. So once again, researchers are unsure about its composition. The planet completes one orbit every 242 days, making its position within its solar system comparable to that of Venus within ours. However, Kepler-69c's host star is about 80% as luminous as the Sun, so the planet appears to be in the habitable zone. 4. Kepler-62f. This planet is about 40% larger than Earth and orbits a star much cooler than our Sun, according to NASA. Its 26-day orbit, however, puts Kepler-62f squarely within the habitable zone. While Kepler-62 orbits closer to its red dwarf star than Earth does to the Sun, the star produces much less light. Kepler-62f lies about 1 in 200 light-years away, and, due to its large size, is within the range of potentially rocky planets that may hold oceans. 5. Kepler-186f. This planet is at most 10% larger than Earth, and it also appears to reside in the habitable zone of its star, though on the zone's outer edge. Kepler-186f receives just 1/3 of the energy from its star that Earth gets from the Sun. Kepler-186f's parent star is a red dwarf, so the alien world is not a true Earth twin. The planet lies about 500 light-years from Earth. 6. Kepler-442b. Kepler-442b is 33% larger than Earth and completes an orbit of its star every 112 days. The discovery of Kepler-442, situated 1,194 light-years away from Earth, was announced in 2015. One study, published in the monthly notices of the Royal Astronomical Society in 2021, found that this exoplanet may receive enough light to sustain a large biosphere. The researchers analyzed the likelihood of different planets being able to carry out photosynthesis. They found that Kepler-442b receives sufficient radiation from its star. 7. Kepler-452b. This world, whose discovery was announced in 2015, is the first near-Earth-sized planet that orbits around a star the size of the Sun, according to NASA exoplanets. Kepler-452b is 60% larger than Earth, and its parent star is 10% larger than the Sun. Kepler-452 is very similar to our Sun, and the exoplanet orbits in the habitable zone. Its discoverers have said at 1.6 times the size of Earth, Kepler-452b has a better-than-even chance of being rocky. Kepler-452b resides 1/400 light-years from Earth. It takes Kepler-452b just 20 days longer to orbit its star than Earth does. 8. Kepler-1649c. When the data from NASA's Kepler Space Telescope was reanalyzed, scientists discovered Kepler-1649c. The exoplanet was found to be similar in size to Earth and orbiting in its star's habitable zone. During the initial data collection from the telescope, a computer algorithm misidentified the astronomical body, but in 2020, it was discovered to be a planet. Kepler-1649c is located 300 light-years from Earth and is only 1.06 times larger than it. When comparing the light that the two planets receive from their stars, scientists found that this exoplanet receives 75% of the light Earth does from the Sun. 9. TRAPPIST-1e. Orbiting the star. TRAPPIST-1 are the most Earth-sized planets ever discovered in the habitable zone of a single star. This planetary system is made up of 7 worlds. Water on most of these planets is likely to have evaporated early in the system's formation, Space.com previously reported. However, a 2018 study found that some of these planets could hold more water than Earth's oceans. One of the worlds, called TRAPPIST-1e, is thought to be the most likely to support life as we know it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.